So this problem of finding the derivative, find the slope of x squared plus y squared equals 1 for any location on the curve has two basic approaches, right? So two approaches. One you would call the direct approach, and the other the indirect. The direct approach is what we've been doing so far. Which will not be used in this section hardly at all, if any. So, but let's see it anyway, just to show how we could use what we know so far. So the direct approach is to express y as a function of x explicitly and use the rules we have so far. To find the derivative. All right. So how would that look? Well, the equation is x squared plus y squared equals 1. So I could easily solve for y here. In this case, I've brought a case where I'm able to solve for y. This is not always the case. Sometimes it's extremely forbidding to solve equations that are relations and solve them for y in terms of x solely. And not only that, not only is it sometimes just prohibitive to do it because of the difficulty, at other times it's well nigh impossible, literally speaking. So here it's simple enough. I'll just subtract x squared from both sides, and I'll take the square root of both sides. That will introduce a plus minus on one side. I'll pick the right side to put the plus minus. I have this expression for y. Now, it's still not a function because I have two differing y values. If I pick an x value right now, and I plug this in here, except again at the endpoints, like 0 for instance, I'll get what we discussed earlier. I'll get two different locations. I'll get positive root 1 and negative root 1, which is plus and minus 1. So that's two y values for one x value, so this still is not a function. But I can split this into two cases. Y equals the positive root of 1 minus x squared, which is the upper half of the circle, where the y values are positive, and I can take y equals negative, the other option, but I got to separate them out. Y equals negative root 1 minus x squared is the lower half of the circle. Okay. So at this point, now that we've got them separated like this, each one is certainly a function, right? Look at the picture. The upper half of the circle is a function. It would pass the vertical line test. The lower half of the circle is a function. It would pass the vertical line test. So we just split our relation into as many pieces as we need that all separately are functions. Okay? Then you just take the derivative in the usual way. So for the upper half of the circle, I call this 1, this 2, then number 1, I could find the derivative, dy dx equals the derivative operator d dx applied to the positive root of 1 minus x squared. Using a power rule, the radical is a 1/2 power, the 1/2 comes down, so I would get 1/2. The inner function stays the same. Power goes down by 1 to negative 1/2, and Now I multiply by the derivative of the inner function, the 1 minus x squared, to complete the chain rule, and I'll get times negative 2x, of course. Clean this up slightly. The 2's will cancel. We'll be left with a negative x in the numerator. This factor will be pushed to the bottom because of the negative exponent, and we'll have a radical down there. So it should look something like negative x, oops, negative x over the square root of 1 minus x squared. Okay, so there is the derivative of the upper half of the circle. And if I want to know what the slope was there, I could plug in any x value is legitimate, and I could find the slope. For example, again, if I plugged in the value of 0, right? Plug in x value of 0, you would have negative 0 over 1. And that would be the slope right there. Right? You would have a horizontal tangent there. We have a slope of 0 for the tangent line there. Makes perfect sense. All right. And you can do the same thing with the lower half of the circle. Not a problem. Matter of fact, in this case, it's extremely simple once you've done the grunt work for the upper half. And that is dy dx for the lower half of the circle, since it's merely the negation of the upper half, right? You just negate all those values. So therefore, the derivative must be just the negation of the derivative of the first one. So I'll just negate this expression here, and without going through all the work over again, applying the derivative rules, we'll have this. And there would be our answer for the derivative of the lower half of the circle. And so now we can plug in any x value we want. If we want to know what the slope of the curve is here, I could plug in this a value to the second derivative down below for the lower half of the circle, and I could find out what the value of this slope is. Right? And again, if you plug in the number 0, for example, you see the second expression down there for the derivative of the lower half of the circle will certainly be 0 again, because down here it's also a horizontal tangent. Right? All right, so that would be the approach, the direct approach to finding the derivative of a relation, is to split a relation into as many pieces as possible that separately each one is a function. Take those derivatives all separately, and then you have the derivative, you have the slope of the curve everywhere, just broken into pieces.